Today we are solving physical chemistry assignment 4. Now I'll proceed with the question number 1. So in question number 1 we are given it is given that there is 1 mole of gas A and 3 moles of gas B in 1 liter and 2 liters container, and we are mixing these gases. So we have to calculate the entropy change in mixing. So we'll first derive the formula for entropy. So the formula for entropy actually comes from this differential equation ds is equals to dq by t. So if you take dq at constant temperature and dq at constant volume, you divided the dq actually here upon t. So at constant temperature you can write dq is equals to minus pdv from the thermodynamic second equation of thermodynamics. So you can write dq at constant temperature will be pdv, and dq at constant volume will be actually dq we can write as nc dt, and for constant volume it will take c is equals to cv, so it becomes ncv dt. So taking the putting the value of dq at constant temperature, that is pdv, and value of dq at constant volume, that is ncv dt, we calculate entropy change, integrate it from s1 s2 v1 v2 t1 t2, we get nr ln v2 by v1 plus ncv ln t2 by t1. This is the formula for entropy change. Now for calculating the entropy change in mixing, we will find the entropy change. We will take some reference point 1, that's for just theoretical purpose, there is no implication in the question, but if they say there is some initial point 1, reference point 1, so it's actually the final entropy change from for reaching to the final state from the reference point, and this is delta S initial, reaching the initial state from the reference point. So when you subtract these entropies, you actually the reference values of volume and temperature will get cancelled in this equation. So this simplifies to this is an expression. Remember this expression, it's very useful actually. So how do you calculate this expression? Basically, like if you find the entropy changes of final and initial, like you'll come upon this, it's given in notes as well, so I won't go with the derivation right now. So if you put the value of n is the total number of moles of gases, so it is 1 plus 3, that's 4. R 8.31, x value it is the value in joules. If you want to take liter atm, you can go with 0.0821, and if you want to take bar liter, you can go for 0.08314. So it's for joule. Then xa is the mole fraction of A. If we put 1 instead of I, or A instead of I, 1 by 4, because 1 mole of A and total number of moles are 4, ln xa, that is 1 by 4 again, plus xb 3 by 4 times ln xb, that's also 3 by 4. So calculating these values, we get entropy change of mixing as 18.701 joule per Kelvin. So that's the final answer. We saw here the formula for entropy here. You don't have to go by the derivation, just remember this. This is the formula for entropy change during mixing of gases. So remember these two formulas, and if you want to go with the derivations, you can see the derivation of this here, and this is quite complicated. It's covered in notes as well. Thank you.
Everyone, now we will do the second question of the chemistry assignment. The question gave us a reaction, not a reaction but a process, that water goes from 27 degrees Celsius to 100 degrees Celsius, and then it converts to vapor, and vapor converts from 100 degrees Celsius to 227 degrees Celsius. The given values are heat capacity of water and vapor, that is 1 calorie per gram and 0.4 calorie per gram, and heat of vaporization is also given to us, and they ask us for delta G, delta H and delta S at all the processes, means at all the steps. So what I did, I first found this step, then this step, and then this step, which are here, here and here. So for the first step, for delta H is equals to m Cp delta T, and Cp is equals to the heat capacity that we got, like that was given to us. But the m here, m is the mass, and what was given to us is 5 gram mole. So that means we need to first convert the mole to grams. So we need to multiply by the molecular weight of water, that is 18, into 5, so we get 90 grams of water. We have 90 grams of water, and now we find the delta H, delta S and delta G. So for delta H, 90 into 1 into delta T, for this is 100 degrees Celsius in Kelvin, and this is 27 degrees Celsius in Kelvin. So the difference would be 73, and 73 into 90 would be 6570 calories. Now for delta S, we use this formula, which is mCp ln T2 by T1. This could be derived from here, that delta S is equals to integration from initial state to final state dq by t. Now dq reversible is equals to mCp dt. Substituting the value of dq reversible here, we get mCp dt by t integration t1 to t2. That would give us the formula we are using here. So now substituting the values, we get 91.53 Kelvin per calorie per Kelvin. Now for delta G, we integrate dg is equals to dH minus T delta S. We are doing this because temperature is not constant at every point in the reaction. Like the temperature is increasing, that's why we use dg here. So now integrating the values, we get delta H is equals dH is equals to delta H, and TDS is equals to Q reversible. Now since Q reversible is equals to delta H, so therefore delta G would be 0. So for this step, for the first step, when the water is going from 27 degrees Celsius to 100 degrees Celsius, the delta G value will be 0. The delta S would be minus 19.53 Kelvin per calorie per Kelvin, and 6570 is the value of delta H. Now for vaporization of water to vapor, we use delta H is equals to ml. Now here an interesting thing is that temperature is constant, so delta S could be easily found here by delta H by T boiling. So delta H is equals to ml with enthalpy change ml. This is mass into latent heat of vaporization, which is given to us as 570 calorie per gram. So using that, we got 48,600 calories. Now delta S, as I told you, that since the temperature is constant, we can use this formula, because delta Q would be equals to delta H here, and substituting the values, we get 130.29 calorie per Kelvin. Since this is an equilibrium, vaporization is an equilibrium process, delta G would be 0. Now for the third step, we can do the similar thing as what we did in the first step. The thing is, we need to just change the value of Cp here and the delta temperature value here. So delta H means enthalpy change, we got as 4573 calories, and delta S, using this formula here again, we get 10.549 calorie per Kelvin, and delta G, as we did here, similar thing could be done here, that delta H is equals to Q reversible, therefore delta G would be 0. So this is the solution for the second question. Thank you.
Look at question number 3 of the assignment. We are given delta G is equals to 13580 plus 16.1 T log 10 T minus 92.59 joule per mole in Gibbs energy. We have to calculate delta H and delta S, and we are given that T is equals to 27 degrees Celsius, that is nothing but 300 Kelvin in absolute scale. So to calculate delta H and delta S, we first substitute value of log 10 T. We are given T is equals to 300 Kelvin. So we use log 10 of 300 and get the value of 2.477. Now what we'll do is we'll have to find delta G. We'll use the value of we got here and substitute it here. 13580 plus T 16.1 plus 2.4 multiply by 2.477 minus 72.59. So we'll get the value as minus 32.703. Now we'll use the equation delta G is equals to delta H minus T delta S, and we'll assume the first one, the one with values, to be as equation 1, and the one with variables is as equation 2. Comparing equation 1 and 2, we can see delta H is equals to 13580 joule per mole, and T delta S is equals to minus 32.7103 joule per mole. So which is basically means delta S is equals to 32.703 joule per Kelvin mole. So we are done.
Hello everybody, we are here with the assignment for question number 4. It is given that the equation of state followed in this question by the gas is P V minus B is equal to RT, and we are given a quantity fugacity gamma, and we are given a relation ln of gamma is equal to sum integral 0 to P z minus 1. Z is here, is called the compressibility. Maybe I write this as this. This we know from our basic knowledge. So this is some constant pressure P, and P dash is some intermediate pressure. So we are actually integrating 0 to P, where P is a constant and P dash is something intermediate in between. Z from here will get, since P V minus B is equal to RT, P V by RT is equal to V by V minus B. Okay. Then, and P can be written as, let me just, Z is equal to this one, and P can be written as RT by V minus B. So for some intermediate pressure P dash, let's assume P dash is, because whatever be the expression, the equation of state will always be followed. So in this equation we'll put P dash, or I directly write it, P dash is equal to some intermediate volume V dash minus B, and temperature would be constant. Now let me make everything in terms of volume. So dP dash is RT by V minus V dash minus B square dV dash. I have just integrated, I have just differentiated these. Okay. Now natural log of gamma is given as 0 to P. So we have converted P in terms of V. So when P is 0, we can see the volume V is going to infinity. We are just making the change of variable, don't get confused. And when P is P as given, so volume is V, some volume V corresponding to this equation. Simple. Now putting the limits, proper limits, Z minus 1. So what is Z minus 1? Z is this guy. So V minus B minus 1 by P dash. P dash is this guy. RT by V dash minus B, and this would be V dash minus V dash, because Z we have to take intermediate Z. Then dP is minus RT by V dash minus B square dB dash. Integrate it, you will get Z infinity to V. This will become, this will go up, V dash minus B, V dash minus B will get cancelled. This will be B by RT, and this will be into now. So RT will get cancelled, and B minus V minus V dash minus B square dV dash. Let me check B, and yeah, it's correct. It is simple integration, nothing else. Let me do it here. This will become infinity to V. This will become B by V dash minus B just integrate it, simple integration. Putting v, we'll get v minus b. Now I am putting v, the actual value corresponding to the p given by the state, and minus, when you put infinity here, b by infinity minus something is b by infinity, that is 0. So you got a natural log of gamma is equal to b by v minus b. Change v, where we were, change v minus b. See, from the equation of state given, we can write v minus b is equal to RT by P. Put v minus b, RT is equal to RT by P here, you will get natural log of gamma is equal to b by RT by P, RT by, and P will go up. So gamma, finally, gamma is, you take power of e both sides, PB by RT, and that, my friends, is the answer. Thank you.
Now I'll solve question number 5. In question number 5, the Haber's process reaction is given, that is the preparation for ammonia gas. So the reaction is N2 plus 3H2 is in equilibrium with like NH3 gas to NH3. So here the question in the question it is given that the equilibrium constants at 300 Kelvin and 500 Kelvin are given, and we are asked to find the enthalpy change for this reaction. So actually you won't naturally come up with the solution if you don't know the equation. So if you use the want of equation here, then only I guess you can find the result. So the equation is something like ln K2 by K1. K2 is, if you take the reaction mixture, this reaction mixture from some state 1, in this case 1 is 300 Kelvin, from state to some state 2, that is 500 Kelvin here, and like these are the reaction constants, these are the states. So delta, so the ln of this is equals to, natural logarithm is equals to delta H by R, gas constant, into 1 by T1, here T1 is 300 minus 1 by T2, 500. So if we put the values here, that's K 500 upon K 300, 1 by 300. So if you go with the calculation, delta H, we shift R here and this term also here, we get finally delta H is equals to minus 205.3 kilojoule per mole. That's it's actually an equation based question. It doesn't require much time also. So yeah, that's the solution for it. If you know the equation, you know the answer.